Good afternoon, everybody. Once again, I'm John Berry, and welcome to the AIPG Texas Section Webinar. Those who want to take the quiz, remember that the quiz will be available immediately at the end of the talk. Today, we have the Executive President of AIPG speaking to us. Aaron Johnson has been the Executive Director of AIPG for 9 years. He's also a member of the Federal Advisory Committee for the National Geologic Mapping Program of the UNECE Expert Group on Resource Management. I'm sorry, I'm having trouble putting words out right today. His degrees are from Missouri State and from the University of Missouri, Columbia, and his hobby is car racing. Aaron's going to talk about the world-class Mississippi Valley type ore deposits of the lower Midwest, their genesis, exploitation, and environmental concerns. And he's also going to have a few words to say about the role of AIPG in assisting and promoting the geologic profession. Go right ahead, Aaron.
John, thank you, and thanks for inviting me today. I really appreciate the opportunity to be part of the Texas webinar. We see this webinar series as one of the crown jewels that we see our sections provide, and the Texas section, of course, is an exemplary section that is a good example of what a section can be, and I think a section that other AIPG sections aspire to in some ways. So I really do appreciate all the good work that the Texas section does and all the hard work that its members do. If you're an AIPG member and you're on the webinar today, and I assume most of you are, I really do appreciate you being members. If you're not, I strongly encourage you to join. AIPG, one of our primary responsibilities is to advocate for geologists and for geology at sort of all levels, sort of internationally, nationally, regionally, and locally. And there have been a few things that have come up recently that I kind of wanted to make people aware of. We just found out this week there's a sort of existential threat to the Indiana Geological Survey. So we're working with the Illinois-Indiana section to try to figure out how we best support their efforts to ensure that the Illinois or Indiana Geological Section or Survey remains a viable and important piece of the geologic tapestry. We also worked a little bit down in Florida. There's been sort of an effort in Florida to do away with business licenses for geologists. And we continue to see sort of the whack-a-mole effort to de-license geologists that kind of arises state by state. It seems every year that comes up. You know, a few years back, it was Texas, and the Texas section did a fantastic job educating lawmakers. And our job as the national section was to support Texas. I think one of the things that I've learned in this position is that legislators want to hear from constituents. And if I come in from the outside, it means far less than when those geologists that work in the state come in, and then we're there to help provide you with some of the resources, whether they're written resources or whether it's letters or whatever it might be. So we have several of those things that are going on right now nationwide that we're kind of trying to keep track of. The other thing that I wanted to just briefly mention is that we have our national scholarship program, and I know Texas has a vibrant scholarship program as well. And between the U.S. national organization and each of our individual sections, AIPG in a given year, it's not uncommon for us to give out north of $40,000 in support for students. And that's one of the largest numbers of any professional organization in the U.S. So geology professional organization. So I think really you as members, you're the ones that make that happen. We can't do that without your support and without your being members and paying those member dues. So I just wanted to thank you for that and to let you know that we want to expand that and we want to continue to make that part of AIPG's legacy. I think I'll stop with the shilling for AIPG there and get on to the business at hand. My PhD work was on Irish type zinc lead deposits. They're carbonate hosted deposits. And the reason that I got interested in them was that I grew up in Southwest Missouri, which is in the edge of the tri-state mining district. And so I'm really going to focus on tri-state because it provides a microcosm of really the challenges and opportunities that we see in some of these world-class Mississippi Valley type deposits. So that's kind of going to be my focus today, and we can use that as a discussion point for some of the other deposits in the lower Midwest, whether it's the Viburnum Trend or the Central Arkansas District, or even some of those deposits that we saw over in the western tip of Virginia, whether it's the Tennessee deposits. They have a lot of the same challenges and the same opportunities. So we'll start just by talking about splitting this talk into two pieces. I'm going to start out with some of the history, and then look geologically at how these things form, what they look like, what some of the structures are that govern them. We'll talk about the mineralogy and some of the trace elements, and then we'll sum up that piece. And then we'll step over into some of the environmental concerns. We'll start out with geology and sort of emplacement and go from there. So this map, that square there in the Kansas, Missouri, Arkansas four-state district outlines what we think of as the tri-state mining district. Really, it's sort of five big sub-districts. You can think of the Pitcher, Oklahoma district here, then the Baxter Springs, Galena, Kansas district. You've got the Joplin district, and then you've got the Neosho Granby district. So this is the primary location of that tri-state district. My family home, the ancestral home, was about right there where my mouse pointer is. So right there in north central Lawrence County, just right on the outside edge. When I was a kid growing up playing Pony League baseball, we regularly played ball against kids from Galena and then down in Baxter Springs. And then we would also travel over to Pitcher to play baseball. I'll have a little story about that when we get there. Each of those little blue dots is the location of an area where some ore was produced, but it's the big squares or the areas outlined in yellow where there was significant ore production. We're talking about, in many cases, tens to even hundreds of millions of tons of zinc, lead, and copper ore that was part of that old tri-state mining district. The first recorded writing that sort of outlined that there might be galena in the area was by William Breckinridge and John Henry Schoolcraft. They were two early explorers that went down into southwestern Missouri in the early 1800s. Schoolcraft is particularly important because he spent some time trying to navigate the major rivers of southwestern Missouri and down into northeast Oklahoma. Did it mostly in a flat bottom boat and recorded in his journal several instances where when his boat would contact the bluffs, you could see the gray streak of galena in the rock. So this was galena that was exposed at the surface. And by 1848, the first prospect had come into production that was in Leadville, which is now northwest Joplin. So if we were to jump back here, we're talking about the first prospect being just about where my mouse pointer there is, just to the northwest of that green dot. The discoveries after that came really quickly. The Granby district opened in 1850, Galena, Kansas 25 years later in 76, Aurora, Missouri in 1886, and then Peoria and Commerce, Oklahoma in 1890 and 1905. By 1905, the tri-state district was in full production, and it routinely was the world's leading producer of zinc and lead. So a huge district that had enormous economic implications for that part of the country. From about 1850 to 1955, that was a regular occurrence that you would see the tri-state mining district as one of the world leaders, if not the world leaders in production. But when mining tailed off, it tailed off very quickly, ending in Missouri in 1957 and being complete in Kansas and Oklahoma by 1970. Although there's a little bit of information that there was some mining going on still in the Pitcher area in 1972, but certainly by 72, all of the mining was done. Now that coincides with the discovery and exploitation of the Viburnum Trend. I'll show you the trend here in just a minute. In 1958, with mining really coming online in about 1960. So if we're talking about those kinds of mines again, we're really looking at the Pitcher, Oklahoma area by 1972 being sort of the end of mining. Structurally, this part of the country is really interesting. You've got the Illinois Basin, excuse me, up to the northeast. That's a primary world-class oil and gas producing basin. Forest City Basin to the northwest. That's sort of a minor player in terms of oil and gas. There is oil and gas present. A lot more coal that was mined out of Forest City relative to oil and gas. And then, of course, if you're from Texas and you're at all affiliated with anything that has to do with the oil patch, you know the Arcoma Basin and you know it well. Now, there are several of these Mississippi Valley type deposits, tri-state outlined here. The old lead belt that was discovered in sometime in the 1750s and was mined off and on until the mid 1900s. And then the viburnum trend here, which was discovered in 1958 and continues to be mined today. The trend, the largest lead deposit in the Northern Hemisphere, as of the last number that I had, they produced about 400 million tons of lead, zinc, and copper ore. You can go underground in the town of Viburnum right about where my pointer is and go underground, go down about 700 feet, and then travel due south in a straight line for over 25 miles without coming up. So it truly is one of the largest deposits in the world. A shameless plug. We'll have the AIPG annual meeting in St. Louis in October, and one of our field trips will be to go underground into the viburnum trend in one of the working mines there. So might be something interesting for you as geologists. So we've got the structure setting here, sort of broadly speaking. We would have had the Ouachita Mountains here off to the south. Geothermal barometry says 15 to 20,000 feet elevation at their peak. I've seen some folks try to get to 25,000, but the numbers really don't support it, and we don't need it anyway to make the ore deposits. 15,000 feet of elevation there will get us plenty of hydrologic head to build these deposits. We'll talk about that in just a minute. Structurally, if we look at the major fault features and fracture sets, most things trend sort of northwest to southeast. Several significant faults, primary among them here, the Chesapeake Fault, which has maybe 1,000 feet of vertical throw and as much as 1.5 miles of lateral offset. That would have been one of the primary fluid localizing features. And then subsidiary to these are a number of joint and fracture sets that tend to trend mostly northwest to southeast, but there are the complementary joints that occur at about a 90-degree angle to that. And we do see that most of these deposits are associated with areas where we've got fracture and joint sets that allow for fluid flow. Stratigraphically, this is the stratigraphic column of Missouri. I shamelessly stole it from the Missouri Geological Survey. I'll give them credit. But most of the ore in southwest Missouri there in the Tri-State District is hosted from about the Reed Spring Formation here. So that's Osagian series rocks, all the way up into the St. Louis Formation, the St. Louis limestone, which is sort of Meramecian series, kind of Mississippian carboniferous stuff. If we were to go over to the southwest part of the state, we see the ore hosting unit is primarily the Bonne Terre Formation down here deep. And one of the things we see about Mississippi Valley type deposits in general is that they tend to be hosted in the stratigraphically lowest clean carbonate. And in southwest Missouri, that often is these shallower Mississippian rocks. We can get you some descriptions here. I think the primary thing to recognize is that we're talking about crinoidal limestones, and that means we've got pretty good porosity. And it's the porosity that's really important if we're going to localize ore. This diagram just shows you ore volumes, and the ore volumes are based on asterisks. 3 asterisks is a primary ore host, 2 asterisks is an ore host, and anything that's 1 asterisk or just an open circle hosted mineralization, but not necessarily at mineable quantities. And so you can see really there are kind of 3 primary formations. The Reed Spring, that's mostly over in Kansas and Oklahoma. You've got the Burlington Keokuk, that's in both the Missouri and the Kansas and Oklahoma districts. And then in Kansas and Oklahoma, you see some more in the Warsaw Formation, both in the Baxter Springs and the Moccasin Bend, those 2 subsets. So It differs a little bit from southwest to northeast. So the further west you go, you have some of that ore localized in some slightly stratigraphically higher units. Generally speaking, we're talking about Mississippi Valley type deposits. We're talking about that middle to Visayan to Upper Ternasian host. Fluid source, for these deposits, almost certainly the primary fluid source is fluid that came through the Arkoma Basin. At its deepest, the Arkoma Basin is 25 to 30,000 feet deep. So the fluids would probably be generated as rainwater falling up in those highlands, the Ouachita Mountains there at 15 to 20,000 feet elevation, so rain and snow. As that melted, it would flow through those basal sandstones, go through the bottom of the Arkoma Basin and be heated, and along its flow path, probably pick up some lead and zinc. And then when it moved up onto the platform, it would encounter the right conditions for precipitation and make an ore deposit. We look at the fluid inclusions, the temperatures are, at the bottom end about 75 degrees Celsius, at the top end about 150, which really corresponds with the hydrocarbon window. So if you want to make an ore deposit in Southwest Missouri, or if you want to, make the oil for the oil fields there in Oklahoma, you've got the right conditions. Zinc source, probably shale. One of the things we know about shales, especially the shales that are present in those sediments in the Arkoma Basin, is they do carry quite a little bit of zinc. And we know that the crystal structure of feldspar is just right for lead to be able to substitute in, often for calcium. So if we're going to liberate lead, we're probably taking it out of the feldspars. If we're going to make some zinc, we're probably taking it out of the shale. And then when we deposit those ore deposits, what happens is those fluids flow up. They come up against a paleotopographic high. So probably the old granitic rocks that were exposed in the Precambrian. Then the sediments are deposited around them. They might become even some of them fringing reefs or little islands in these Cambrian seas or in these Mississippian seas. And when that happens, later when the fluids flow through, they get focused because the crystalline basement rocks are not nearly as permeable. And if we can focus those fluids and we can find a little sulfur, we can make an ore deposit. So that's basically the model. We're going to drive that water through, we're going to move it up onto the platform, and then if we've got some sulfur, we're going to make an ore deposit. Now the question is, how do you move lead and zinc in these fluids and not precipitate them out as they move along? You have to hide them from the sulfur, or you have to have a fluid that doesn't have much sulfur in it, one or the other. And we'll talk a little bit about maybe which one of those it really was. If we go to Pitcher, Oklahoma, there are a lot of documentation there that when miners would open up into these vugs, and we're thinking about vugs that are room sized often, so vugs that are the size of a large room, or even in some cases, the vaulted ceiling that you have in your house, right? We're talking 15, 20 feet high, 20, 30 feet wide. When they would blast into those vugs, oil would gush out. And there are many, many cases of miners recording that and geologists recording that in their notes. And then there's the presence of a lot of bitumen as well. So we know that these brines sometimes carried oil with them. And if we look at the fluid inclusions, the chemistry, the chlorine to bromine ratios look like oil field brines. The total overall salinity looks like oil field brine. The trace element chemistry looks like oil field brine. So there's very good evidence that the same brines that were associated with making some of the oil that we see in the sort of the northeast Oklahoma oil fields may also have been associated with making these ore deposits in southeastern or southwestern Missouri. One of the big questions is how you deposit this stuff, right? You've got, in some cases, hundreds of millions of tons of zinc and lead. How do you make that deposit in a concentration that's mineable? There are a couple of ideas. One of them is, one of the most important things is that if you look at the temperatures, you can't have bacterial sulfate reduction. So if you were transporting these metals with sulfate, and then on site, the fluids came into this area where there's a lot of bacteria, maybe it's a reducing environment, you can't really make bacterial reduction happen because at 150 degrees Celsius, you kill the bacteria. So it has to be something else. The simplest explanation is that the sulfur is already present. You're liberating the sulfur. If you're making oil, you know that there's plenty of sulfur around because there's a lot of sulfur that can be associated with oil. So we've got a sulfur source, and then that means how do we move the lead without the lead combining with the sulfur before it gets to these locations where it can precipitate out? Well, one of the things that you can think about is you're just going to cool that fluid off. If you cool it off, you're going to destabilize these complexes and you're going to allow the lead and zinc to see the sulfur. And if it's cooling, because quartz is really soluble at high temperatures and especially at low pHs. If you've got low pH and high temperature, you can dissolve a lot of quartz. Well, when you cool that fluid off, you should deposit a lot of quartz. Now, I didn't put this in the talk, but as I thought about it this morning, I felt like it was important. So lead and zinc, they really like sulfur. I really like cake. My son graduated from high school this weekend. We had a lot of cake. I really like cake. You put me around cake and I'm going to eat cake, and it's really hard to stop me from eating cake. The only way you can stop it is to make sure I don't know there's any cake. That's it. You pretty much have to hide the cake from me. Well, zinc and lead are like that when it comes to sulfur. So you have to hide them from the sulfur. And the best way to do that for zinc and lead is to combine them with chloride ions. They make something called a complex. Lead especially, it's called PbCl4. It's got a -2 charge, and lead will just hang out with chloride all day long. And so if lead's surrounded by chloride, it doesn't know that there's sulfur present. So the lead can float right along, there can be sulfur right next to it, but because the chloride's blocking its view chemically, the lead doesn't know it's there. Zinc is the same. It makes a ZnCl2 complex. So lead and zinc, chloride does for them with respect to sulfur what my wife does for me with respect to cake. Tries to keep me distracted so I don't know there's any cake, so I don't eat too much. But if we cool that solution off, the chloride doesn't want to hang out with the lead anymore. At lower temperatures, chloride would rather go hang out with sodium. And when that happens, the lead now can kind of see the sulfur, and the lead starts to react with the sulfur and make galena. The zinc starts to react with the chloride, and it makes sphalerite. And when my wife gets distracted because her mother is there, I get to see the cake. Now, for me, that's not necessarily a good thing, but if you're making ore deposits, anything you can do to concentrate the fluids in a specific location and then destabilize that complex is going to mean that you can precipitate a lot of valuable material in a very small place. So if it's cooling, our ore deposits should be full of quartz. It could be mixing. We could have one fluid coming in from one location and one fluid coming in from another. We've got sulfur in one fluid and metals in the other, and we make an ore deposit. This is the Reese's peanut butter cup option. We've got chocolate in one hand and peanut butter in the other. When we mix them, we get our chocolate in there, peanut butter, and we make a Reese's peanut butter cup. Well, if we mix the fluids, we make an ore deposit. But in this case, we shouldn't see a whole lot of quartz because it's not about cooling, it's about mixing. So keep that in the back of your mind. All right, so here we are, same photograph. We've got the Forest City, Illinois, and Arkoma Basins. We've got the Tri-State District here in Southwest Missouri. When we look for evidence of fluid flow, we see abundant evidence that we've got south to north fluid flow out of the Arkoma Basin. Dave Leach did some great work at the USGS, really starting in the mid-'80s and going through the mid-'90s, where he documented very clearly that we had south to north fluid flow. And for this whole Tri-State District over here, it absolutely looks like south to north flow. When you get over into the Viburnum Trend and the old lead belt in the east side, then fluids look like they're coming out of the Illinois Basin and things get a little complicated. But for the southwest part of the state, and even for this central Arkansas district down here, that south to north fluid flow is very evident. Paragenesis is just a fancy way of saying order. What's the order of emplacement for the minerals? Now, you might think that chemically, the order of emplacement is going to be which metal likes sulfur the most, which one has the lowest K value, the lowest solubility product, because the least soluble mineral should precipitate out first. And you should think that, but that's just wrong. And it's just wrong because it's really about geochemical abundance. the most abundant metal tends to see sulfur first. So if you've got 1,000,000 zinc atoms and you've only got 1 lead atom, you're going to precipitate out sphalerite before you precipitate out galena. And that's what we see, right? The paragenetic sequence is uniform throughout the district, and it's always dolomite first, followed by sulfides and jasperoid. And jasperoid is fine-grained quartz. Zinc sulfide always comes out before the galena comes out too. Once we get that first stage, we get a bunch of pink dolomite. Sometimes it's sort of that Baroque dolomite, the bladed dolomite. Sometimes it's not. And then we get the main stage sulfide minerals, and we always have sphalerite before we have galena, meaning that we had more zinc than we had lead. And we see even more jasperoid. And there are places in this area where if you go start collecting rocks, you'll see chert breccia. Chert was common in the limestones, and as the limestone dissolved, the chert would pile up, and then it would get cemented back together by jasperoid. So you have these quartz cemented breccias that are part of this hydrothermal system, and we see multiple volumes of quartz compared to the amount of ore. So it's a 3, 4, 5, 6 times as much quartz coming out as we see zinc, lead, or copper. Once that main stage is done, we get some chalcopyrite, and there was enough chalco to mine copper. And then we get the gangue sulfides, right? We get the pyrite and the marcasites that come out. And that becomes important later because we have some acid mine drainage. And then at the end, we get some dolomite, some sulfides, and some more quartz because the fluids are cooling and the quartz is really dropping out. And then at the end, we get these huge volumes of calcite. And if you can just peer at the background here, right up at the top, there's a fella standing right here, and you can kind of see his head. And then up here at the top, these are calcite scalenihedra. And that's for scale. That's a 12-inch tall human head. I've seen examples of these scalenihedral calcite crystals from the tri-state district that are as many as 18 inches tall from base to point and 10 to 15 inches in diameter at the base. So truly remarkable in terms of the size and scale of the crystals that were deposited. Ore geology straightforward, primary ores, sphalerite, galena, chalcopyrite. The gangue minerals, the stuff you throw away, pyrite, marcasite, all the carbonates, and more quartz than you can shake a stick at. And then in the oxidized zones, because these are shallow, there are reports in some of the mines of tree roots, of encountering tree roots as they were mining. Oxidized groundwater would interact with these deposits on a regular basis. And where the deposits were oxidized, you find smithsonite, that's a zinc carbonate, hemimorphite, you might know it as calamine, that's a zinc silicate, and then cerussite, which sounds like a fake name for a knight in a storybook, cerussite, go save the fair maiden, but it's actually the lead carbonate. And so you do see some of those examples. Those are minor, but when you find them, they're pretty valuable because they're very easy to process. Trace elements are critically important here. Cadmium is not good for people. People and cadmium don't mix, and 7,000 parts per million, that's 0.7%. There were locations where the cadmium concentrations were that high. Gallium, germanium, and indium, we do see in some of the tailings piles in the Pitcher area especially, that those are now mineable concentrations. And I found out about 6 months ago that about 800,000 tons of tailings had been sold to be processed for gallium production. So this has become a sort of secondary mining option. So the trace elements become very valuable. So just to sum it up then, it's just to summarize this first piece. We've been mining, we mined there for a little over 100 years, haven't mined in the last 50. There is still ore in the ground, but with the development there and the environmental problems, I don't think we'd ever see mining in Southwest Missouri, Northeast Oklahoma again, unless we really got to be desperate for material. We've got an Arkoma Basin fluid source. We've got metals coming from sandstones and shales. And then as the solution cools, we're making ore deposits around these basement highs. We've got about 10 to 15 times as much sphalerite as we do galena, and we've got about twice as much galena as we do chalcopyrite. We do see oxidized ores. And I didn't mention this earlier, but every once in a while, you'll find a location where the galena contains enough silver that if we process the silver out of it, we can make a little bit of silver. Not as important in the tri-state district But if you go on the field trip to the viburnum trend with us in October, there have been times that it was the silver that kept the viburnum trend open. So significant amounts of silver are possible. Cadmium, gallium, germanium, indium, those are the big trace elements. And I want to note, there's a guy that was at the University of Missouri campus in Rolla for about 40 years. His name was Dick Hagnai. I think of him as really probably the godfather of Mississippi Valley type ore deposit studies in Missouri. And he found a mineral called greenockite in the 1950s in ores near Commerce City, Oklahoma, or Commerce, Oklahoma. Greenockite is cadmium sulfide. It is a primary cadmium sulfide, and that's going to become really important when we do the second part, which is to talk about some of the environmental problems that we see in the old tri-state district. I'm not going to read you the full outline here. I think you guys can read. I will just say we're going to kind of walk through this stepwise, and we'll finish up maybe with some recommendations is too strong because really the recommendations should come from the state, but some things that I hope we'll see happen as we move forward with remediation. All right, so Superfund. 4 primary Superfund sites in the old tri-state district. That's the Cherokee County, Kansas site, that's southeast Kansas, and the Tar Creek, Oklahoma site, that's northeast Oklahoma. Those were both established more than 40 years ago, and cleanup is ongoing. The Dunweg Oronogo site was established in 1990, and cleanup continues there. And then the Neosho Granby, Missouri site was established in 2003. So none of these sites are considered completely closed as yet, although I think maybe we're getting close in some locations. And now we'll go back to our same map, but instead of showing ore deposits, we'll show Superfund sites. Here's Tar Creek. Here's Cherokee County. The Oronogo Dunweg site is here. And then the Neosho Granby site down here. So we'll see that that corresponds really almost 100% with areas where we had the highest concentration of mining. Primary issues, look, we've got acid mine drainage, and we've got a lot of metal movement because zinc, lead and cadmium, they like to move best when pHs are low, and acid mine drainage makes for low pH. So we move those metals into wells, and we move them into surface impoundments as well. What happens is some of the underground mines get flooded, the water is extremely acidic, and those metals move out into unmined areas, and we might just happen to have someone's municipal well right here. All of a sudden, that municipal well is contaminated. Same thing with some of these surface impoundments. We actually see the precipitation of those metals into the sediments in these surface impoundments. And we do see quite a bit of mobilization. Pitcher High School, it's closed now, but before it closed, they moved the well that supplied the high school with water 3 different times because of low pH and metal concentrations. A lot of subsidence. These mines were shallow, in some cases less than 50 feet of overburden between a mine stope and the surface. This is southeast Kansas near Baxter Springs. The remediation here also ongoing, but that's a mined area that has subsequently undergone collapse, and we're kind of looking at the water table, and that brown color is acid mine drainage in the water table. In Missouri especially, a lot of the mines had their own smelter on site, and these were not highly efficient smelters. They were almost pre-smelters, but anytime you do smelting, you can volatilize lead, zinc, and the associated metals into the atmosphere, and then they rain down onto the land surface. So we do see smelter contamination. We see soil contamination in every district, and we do see documented effects in fish, especially in Tar Creek running from Kansas into Oklahoma. If we look at what's going on at the surface, we're seeing a lot of progress. One of the things that has happened is these mined areas, especially in southwestern Missouri and the Joplin area, have been turned into surface recreational use areas. A lot of hiking, a little bit of sort of off-road biking, and maybe even some off-road motorcycling going on, but primarily hiking. And if you look around, other than the occasional bit of the mine processing plants that are left, it's been mostly remediated and revegetated at the surface. So the big tailings piles are mostly gone in southwest Missouri. Still a little work to do in Oronogo. This is one of the tailings piles, and just for scale, that's your standard, 25, 30-foot tall telephone pole. So you're still talking about millions of cubic yards of material that remain to be removed. This is Pitcher, Oklahoma. Pitcher is not as completely remediated, primarily because they had a larger tailings footprint. The tailings are also much more fine grained. That is not an out of focus photograph. That's windblown dust from those tailings piles. If we look at sediment metal concentrations, and I'm not going to beat this too much, I just really want to outline here, this is what's called a threshold effect concentration. That's a TEC, and that's the concentration above which we know there will be effects. And then a probable effect concentration is the concentration above which effects are going to be likely. All I want to point out is that everywhere we sample, especially in stream sediments, we see extraordinarily elevated metal concentrations. And one of the most difficult aspects of this cleanup is that the sediments tend to concentrate those metals. When they get into the water, they react with an oxide, and they'll tend to precipitate out as a zinc oxide or a lead oxide or even sometimes a lead sulfide. And then they get concentrated in the sediments. So they're constantly being renewed. So that concentration is really hard to manage. So sediment metal concentrations are very high. We also see some pretty high concentration in floodplain soils. And floodplain soils, we have a lot of those plants that like to cycle through a lot of water, and that means that they're likely concentrating some of these metals. Near Pitcher, Oklahoma, we get a lot of wild onions, and wild onions love cadmium. For whatever reason, the wild onion bulb concentrates cadmium, and then because the folks in Oklahoma see wild onions as a spring delicacy, they go out and they pick the wild onions and they eat them in the spring, and they unwittingly give themselves cadmium toxicity. In 1995, there were 3 kidney dialysis stations in the county where Pitcher, Oklahoma is located for 35,000 people. So one of the things we know is cadmium is really hard on the kidneys, and one of the probable pathways was the spring harvest of those edible plants, resulting in some cadmium toxicity. Biology impacts, look, downstream biodiversity in every one of these locations decreases, and it is like clockwork. We use mussels as sort of a canary in a coal mine, and there are stream reaches where there are no mussels. No freshwater bivalves of any kind are present for miles. And we see that not just in mussels, we see it in midges and amphipods and crayfish. All the invertebrates, we see it. And we actually see it with some species of fish, especially gar. We see reduced fertility. And if you look at the population and you start to survey them, you see that there are far more female fish being produced than male fish. So there may be an endocrine disruption going on here where offspring tend to more often be female. So biodiversity downstream is always impacted, and it's always negative. We've also seen some effects, especially in migratory waterfowl. If you take waterfowl, we see elevated blood, liver, and kidney metal content in all of those waterfowl. And there are documented cases of the zinc concentration being so high for some of these birds that we have fatalities. We do have documented cases of avian zinc poisoning, and that's primarily from bioaccumulation, right? The midges pick it up, and then the fish pick it up, and then the birds pick it up. But to date, there really aren't any detailed biomagnification studies just yet. There's a guy named Rex McAlilly who works for the USDA who's been working on some of that stuff, but to my knowledge, Rex hasn't completed those studies yet. If you look at humans, it's not the best place to live. We look at Superfund towns relative to towns that aren't part of Superfund, and we look at blood lead levels, and they're up everywhere. And we know that blood lead leads to developmental delays, but it also leads to behavioral problems. And so we see higher incidences of things like ADHD. We see lower reading literacy scores, and we can tie those to lead contamination. If you go to Galena, Kansas, before Superfund, we had higher incidences of stroke, kidney disease, skin cancer, heart disease, anemia. And Galena was one of the most heavily impacted towns. We see higher death rates from all of those things associated with heart disease in the Superfund towns. And it's probably because of the link between the heavy metals to kidney disease and high blood pressure that's driving. Water, a lot of water impacts. We get a ton of leaching and we get a ton of acid mine drainage. Carterville, Missouri, and Pitcher, Oklahoma, probably two that are the most heavily impacted. This is Carterville, and this photograph was taken just a couple of years back. Even though the surface remediation is considered to be complete, the acid mine drainage continues. Sorry, let me back that up. That was Tar Creek, Oklahoma. And again, you can see with Tar Creek, here you see the high water level now, really with a lot of that bright red-orange acid mine drainage. The mitigation strategy here is pretty straightforward. You take carbonate rocks because you've got huge volumes of carbonates at the surface in Missouri, Oklahoma, and Kansas, and you use it as riprap along these streams because when the water interacts with the carbonate, it's going to raise the pH, precipitate out the metals, and neutralize that water. And that works until those pieces of carbonate material get completely coated with iron oxide. And at that point, the water doesn't interact with the limestone anymore, so the pH isn't mitigated as readily. So that iron oxide armoring is a real problem. This is riprap in Carterville, and you can see it's actually probably fairly recent, but it doesn't take long for that iron oxide armoring to occur. That bright red staining is actually iron oxide minerals that are precipitating on the surface of those carbonates and then protecting the carbonate from the water so that the water doesn't get neutralized as easily. We also see a lot of flocculates of unknown composition. I haven't seen a single study yet that has sampled that material, that has sampled that material and tried to determine what is the composition. It's just some kind of precipitate. And I think it's mostly money. I think people care and I think they're aware, but I think they're so overwhelmed with the amount of work to do and the budgets that they have that in the grand scheme of things, what that is kind of minor. If you know somebody in geochemistry in an undergrad school, they're looking for a project, I think flocculate sampling project and trying to map out the concentrations, there's a great little student project there. Dust is a real issue. So we'll go back to that picture from Pitcher, which is really confusing to say, picture from Pitcher. And we see that windblown dust. This is on the west side of a little dirt road. Prevailing wind direction is west to east. That's the east side. It doesn't look like much to you unless you're a farmer. Those are soybeans. And that's a soybean field being coated in wind-blown cadmium-laden dust from the tailings piles there in Pitcher. And this is an old processing facility back here in the back that's been abandoned and mostly torn down, but not remediated. By locality, if we look at remediation, go to Cherokee County, there are 9 subunits. The Galena subunit is pretty much done. They built a new water supply. They did soil remediation. And what we've seen in Galena is the life expectancy and the health impacts are disappearing. And so we're seeing Galena start to look more like any other typical Southeast Kansas town in terms of all of those health problems that were associated with mining or with the mine tailings. Spring River Basin runs through Galena. There's a feasibility study now to look and see if remediation in the Spring River Basin is feasible and what that would look like. Go to Baxter Springs, 400,000 cubic yards of waste removal. That has been awarded since this was put together. The tree subsite, about 500,000 cubic yards of waste has been removed. And then if you go to 3 other sites, those are complete, although they were damaged by flooding and then subsequent drought. So the Kansas Department of Health and Environment had to go back in and repair those sites. But again, we're seeing that the health impacts are reducing, sort of regressing back to the mean. Tar Creek, they're working on a feasibility study for the Kansas side, but they have no strategy to remediate. Tar Creek is among the most heavily impacted watersheds in the lower Midwest. Go to Missouri, go to Oronogo-Dunweg. In a 10-year stretch, blood lead levels dropped from 14% of children having high blood lead levels to 2%. And that number has even gone down since. They moved a lot of mine waste, 25 million yards, and there's still probably another 10 to 15 million yards left to be removed. Remediated well over 3,000 properties. That included supplying some homes with fresh water, bringing in clean topsoil. And the Spring River runs from Kansas into Missouri. So that basin subsite is in feasibility study there as well. So not sure exactly if that'll get started and when. Oklahoma is probably the most heavily impacted for a variety of reasons. The primary among them is that the ores in Oklahoma contain more cadmium than the ores in Missouri or in Kansas. At Tar Creek, they've done significant groundwater remediation. They plugged nearly 100 wells that went through the mine strata and then were contaminating the underlying aquifer, so they got that plugged and cleaned. They're still working on additional wells, and they were working on connecting more residences to city water where they could, especially in Commerce. Did a lot of soil remediation and are continuing to identify properties for soil remediation as well. And one of the biggest things was there were hazardous materials that had been just abandoned at the old Eagle Pitcher office right there in Pitcher, and they managed to complete that. Now in Oklahoma, they did move on to removing the chat piles. I'll show you some pictures of those in a minute, because the chat that we saw, they actually used that to pave the baseball field. So when I played ball, instead of having that nice sort of red dirt infield, it was gray. And when you slid into second and you got grit in your teeth, you were getting mine waste in your teeth, but nobody knew, right? So we moved a lot of chat. They've paved over some of those old facilities. And to this point, that number 7 million should be closer to 10 million now in terms of the mine and mill waste. In 2007, they started relocating residents of Pitcher. And that went on until about 2013. And then in 2013, Pitcher got hit by an EF4 tornado. And the last time I was through Pitcher a couple of years ago, there were 2 residences left in the city. So Pitcher pretty much is a ghost town now. So I think this piece of it is probably the relocation and property buyback piece is probably complete. One of the most interesting things is the Catholic 40 site. Catholic 40 is a creek site. It runs right through the heart of the Quapaw tribal lands. And the Quapaw took the lead on that stabilization and remediation. And it really was the first remediation provided by a tribe on tribal lands. And that made it kind of unique. And the script got flipped. Typically, it's the feds that come in and they oversee the projects, and then they let contracts to the states, and the states find the contractors. Well, in this case, the tribe, because that land was significant to them in terms of their culture and heritage, they took the lead. And it's a wonderful example of how you can flip that script and put some of the local population in those positions of taking charge and then working inside that same structure. There's also some remediation going on by University of Oklahoma. They're looking at sort of passive wetlands as a treatment for some of this acid mine drainage. And that seems to be working pretty well. It's a pilot project, and they're hoping to scale that up. There's also another subunit that's going to deal with how they manage surface water and sediment, and that's in a feasibility stage study. It's complicated because cadmium, lead, and zinc partition into specific compounds, and they occur at varying concentrations depending on which Superfund site you're in. Add to that you have a huge dust management problem, and these metals, like any charged surface. Anything that's got a charge on the surface, clays, quartz particles, and things like that, the metals are going to want to stick to it. And that means that you have to be aware of the way those metals may precipitate out. You also have enormous unmapped mine areas. Remember, this mining here started in 1840. No one was mapping those mines. No one mapped the surfaced extent. When they turned US 71 into Interstate 49, they spent 3 years with ground penetrating radar trying to identify mined areas that they would then have to subsequently engineer around. You do have watershed scale impacts, and those vary. The impacts for Tar Creek are different than the impacts just over the divide for Spring River. So that variability means that a one-size-fits-all approach isn't necessarily going to work. Probably the biggest one is, because we're in tribal country, we have 4 layers of government that all have to communicate and talk to each other. And you and I think we all know that at the best of times, governments don't communicate well with each other. So throw in high pressure, Superfund, health impacts, and you've got a recipe for a really difficult remediation. So what do we do? Well, look, I think Oklahoma's passive treatment, I think that's a good idea. It worked really well in Virginia, where I used to live. We built a wetlands treatment system, and it was incredibly effective. You just have to be able to scale it up. This is what one of these things looked like. That's a Studebaker being dissolved at the water line by low pH water. But we do see that these freshwater plants, they tend to do a really good job of sequestering those heavy metals in their root structures and raising the pH enough with some other treatment that you precipitate the metals out. Some of the surfaces that have been covered by chat need to be paved. If you look here, those are the baseball field lights right there. I used to play ball on that field, and at one time I leaned in to pitch to this kid, and his eyes were rapidly moving back and forth. And it turns out that one of the symptoms of heavy metal toxicity in kids is that it causes the muscles that govern eye movement to twitch. Now, I didn't know that, but that was a kid that probably had some sort of heavy metal issue. If we aerate these things and enhance them, we're going to do an even better job, because by aerating, we're going to make oxides and we're going to pull even more metals out of the water. And I think probably more than anything, to get all the stuff that's at the surface and exposed, get it removed. We're just a contract let about a year ago to take 800,000 tons of that material and process it for gallium. So they're moving in the right direction there. And you can see here, that's the same spot there in picture. You can see that they've got a lot of that material staged to get it moved. One of the things that is being worked on as well is whether or not you can use fungi to remediate some of this material. And once you remediate it, how do you process those fungi so that you don't have to worry about just basically transferring that contaminated material from one spot to another. I think more than anything, cooperation and communication will continue to be key, especially in Oklahoma. And if we can get more examples of finding ways for the federal agencies and the state agencies and the local agencies and the tribal agencies to work together, I think we'll see a much more effective remediation. And so I think that Catholic 40 site where the Quapaw really took the lead, I think it's a great example of what can happen when you're willing, if you can get people to be flexible and to be less territorial and dogmatic. I think that also means that it's harder to complete things in some locations. Some of it's timing, some of it's financing for sure. Some states finance their programs better than others. But I think at the end of the day, cooperation is going to be one of the things that really, really becomes important. I also think that mapping out the presence of the old smelters, it would be worthwhile, because the smelter areas and the waste disposal sites tend to be the hotspots. And if you can deal with the hotspots, then it makes it a little easier to mitigate immediate impact. Acid mine drainage is going to be an issue for 100 years because minerals break down, and you've got oxidizing groundwater, and you get 50 inches of rain a year there. So unless you can completely isolate that pyrite and marcasite from groundwater, you're going to continue to have acid mine drainage, and you're going to have to treat it if you can't stop it at the source. The other issue that really comes in here is that this is a karst region. And so in addition to all of the environmental challenges, when that material gets into the subsurface, whether it's acid mine drainage or metal-laden waters, it tends to spread rapidly because of the karst nature of the subsurface. And so that's a complicating factor. I owe a lot of thanks to a lot of people. I tell you, Joe Dom at the Kansas Department of Health and Environment, he answered a lot of my questions. And then I didn't list them here, but the Association of Missouri Geologists also, I owe them a debt of gratitude for a lot of the folks that they put me in contact with to answer some of my questions. And with that, I'd be happy to try to answer your questions.
Thanks very much, Aaron. That was very, very interesting indeed. And makes you a little scared of the environmental problems associated with all mining districts, which I've had to deal with too. So,
one of the things that I would say to that end, John, is that I think we're learning now that if it's the kind of an ounce of prevention is worth a pound of cure. If we do more work on the front end, it makes it a whole lot easier on the back end because we're going to make a mess. We have to have materials, and we're going to need lead, zinc, and copper, but also lithium and cobalt. We're going to need those things as we move forward. So if we do more due diligence on the front end, maybe things don't look like this on the back end.
Right. And one of the issues is the volume of production goes up all the time. So if you're losing 1% of your ore to the atmosphere at 1,000 tons a day, and you still have 1% losses at 1,000,000 tons. You're
Right.
and I've seen that. I mean, I worked. I had a exploration area downwind of a major smelter, and I had 0.5% copper in the soil, and I had green copper minerals growing on every cut root branch and tree branch. And I went to the
Yeah, we kind of call that the law of large numbers, right? That
yeah
1% of 100 dropped on the ground doesn't seem really that big, but 1% of 10 million is a lot.
yeah. They said, "Boy, we're the cleanest smelter in the world. We recover 98.5% of everything." And I said, "Well, how much are you making?" And they gave me the number, and I worked out they were losing 5,500 tons of copper a year out the chimney.
Oh, holy cow.
So I mean, this problem is inherent in the growth in economic growth.
Yes. And it's a reflection, right? So one of the things that this mining district is it shows us what was. When we started mining in 1840, mining was primitive, processing was primitive. If we mined that same area today, it would look very different at the completion of mining. And if we started mining it 100 years from now, it would look very different than it would look if we started mining it today. I think one of the things that the general public, when I talk to people that find out I'm a geologist, the first thing they say is, "Oh, you look for oil." And I say, "Well, no, really, I look for minerals." But they have a vision of mining that, if you ever saw the Clint Eastwood movie Pale Rider, came out in 1985, and they're doing hydraulic mining. They're taking these big hydraulic hoses and they make a pretty big mess. That's the vision most people have. They have a vision of mining that's the 1880s ghost town style mining with the blighted land surfaces and the piles of rocks everywhere and nothing grows. And if you were to go on this field trip with us to the Viburnum Trend, you won't know there's a mine until we pull into the driveway
Mhm.
because the surface impact is minimized now. They try to capture the dust, they try to capture the water, because we've learned over the last 100 years that we don't want to make these enormous messes. We live there too often, us as geologists and as the people that work in the mines. So we don't want to mess the surface up either. We have to live there.
One thing I wonder whether that could be done in these tri-state district is where I worked. There were huge amounts of very high tailings piles containing from the copper concentrator, and they were found to be economic to reprocess. So when they processed them, they stuck what was left back into the mines, and it's very fine grained, so it's almost impermeable. And I wonder if that isn't a partial or couldn't be a partial answer to some of the acid mine drainage from open underground workings.
There is some work going on now to pump. So some of these are fine grained enough they can make a slurry out of it and then pump it back underground into some of the open spaces. And it serves two purposes, right? One is it limits water flow, and the second is it limits subsidence, right? Because you're resupporting those underground workings. And there is some reprocessing going on, although right now it's not reprocessing for zinc. It's reprocessing for gallium mostly.
Yeah. 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 Okay.
Yeah, so I think there is something to be said for that. If you ever get the chance, if you're up on the UP in Michigan, there's a mine project up there called the Eagle Mine. It's run by Lundin Mining out of Canada, and they take their tailings back into the subsurface workings and combine it with grout and grout it back into place.
Right. So there are a bunch of questions here in the chat. Do you want to address them? Robin asked a related question to mine. That is, where does the waste go when they remove it?
Yeah, so two places, well, three places. So one, some of the waste is purchased and reprocessed, and I don't know where the facility puts the material after they've reprocessed it. I just don't have that information. I really probably should have looked it up. Some of it goes back underground. It'll get pumped back under as a slurry, and then some of it actually gets taken off and reprocessed or decontaminated, and then it's buried. Some of that material is just, it's simply buried. And I think they assess that for pyrite content because they really don't want to bury it and then create an acid mine drainage issue. So when the pyrite content's low enough and the cadmium content is low enough, that material simply gets buried.
And here's somebody, Bill Agee, has a more of an exploration question. I think sulfur isotopes on sulfides might provide some insight on sulfur source. Light S16 values are biogenic source, heavier ones are thermogenic sourced and associated with hydrocarbons. Bacteria go dormant at high temperatures, but they hang around and metabolize SO4 into H2S. And then he says the same for lead isotopes, and he used both the zinc and lead isotopes on his thesis work in mineralization of salt domes in the Gulf Coast.
Well, that's fantastic because we don't have a lot of information from the tri-state district with respect to sulfur or lead isotopes because there's just so little material left. It was closed up before that really became a common tool. We've got a lot from the viburnum trend. And in the viburnum trend, when we look at sulfur isotopes, we see both biogenic and non-biogenic signatures and significant signatures. So a significant amount of biogenic sulfur reduction in the trend, which would suggest that there could have been biogenic sulfur reduction in tri-states, but it's just a hard analysis to do because there's just not much material left. What's left is in museums, and they don't want you coming in and drilling holes in their samples. Yeah, that's a wonderful point, and I really appreciate it because my training is mostly stable isotope chemistry, and I didn't really want to dive into that too deep, but I'm glad somebody brought it up because it is a wonderful tool, and he's exactly right.
Okay. There's very interesting mineralization in the salt domes. I've been down the one just outside Houston and seen it. So, have any PRPs been held responsible? This is from
that's an interesting question. The one company that has been held responsible to a degree has been Eagle Pitcher. Eagle Pitcher has been held to some degree responsible. If I remember right, St. Joe Lead had purchased a couple of properties there, and then they took on some responsibility as part of that purchase. But primarily, especially the very early production, a lot of these were wildcat miners. It was somebody that saw galena at the surface, and they just started digging, and pretty soon their brother came digging with them, and then the next thing they knew they had a mine and they'd incorporated it. So the answer is it's very rare, but in a couple of instances it's happened.
Then I don't see another question here. A lot of flattering comments.
I see a couple here. One from Bill Agee again. He was asking about direct mineral extraction as a way to remediate contaminated groundwater.
Yep.
That's an interesting question. And because we're not dealing with brines, if we had brines and we could make some of those complexes, we probably could try that. And in fact, I seem to remember there was a guy named John Yang at the University of Missouri many years ago, and he looked at whether or not you could inject brine solutions to pull the metals out of the sediments and then harvest the metals by destabilizing those brine complexes. And I don't think he ever came up with a way to do it economically. But I like the way Bill's really thinking like a geochemist here, and that kind of makes me feel good. But being a geochemist myself, but yeah, I mean, he's exactly right. Could you find ways to treat the water and pull the mineral out and then sell it? Yeah. And then Matt Shoemaker, I see your question. Matt had asked if the tails that are pumped back underground, is it fine limestone or Portland cement that's added? I can tell you I don't know the answer to that question, but I'm perfectly happy to reach out to my contact over there at the Kansas Department of Health and Environment and see if he knows. But I know it is a slurry they pump underground. It would make sense that it was mixed with something that was concrete, Portland cement based to try to minimize fluid flow once it's in.
The other
Um,
one I seen was from Steve Stokowski. Does the sphalerite contain a substantial amount of silver?
oh, yeah.
So it's really interesting. Early on, um, when they did start seeing silver there, they almost always attributed it to galena. And then when the geochemists really got involved, it turns out that it probably is being carried a little more, especially in the tri-state district, in the sphalerite. And they did from time to time would have runs where the sphalerite silver concentration was high enough that they would process it and try to pull it out and sell it. Absolutely.
You talked about the quartz mineralization, and we took an AIPG field trip down one of the Central Tennessee lead zinc mines once, and I brought back a piece of core that I tried to carve into a statue, and I was amazed to find that this piece of core, which looked like dolomite, was actually almost entirely silica when I started working on it. It took me months to carve it. So I was going to ask Aaron. He's going to quick bum. So my question was, Aaron, is all the silica that you see associated with the mineralization in Missouri sort of obvious? Silica, quartz, chalcedony, or do you get a lot of impregnation of the dolomites around the ore body?
No, it's almost always chalcedony and jasperoid, and it's pretty easily identifiable.
Okay.
You don't see a lot of that sort of layer by layer or molecule by molecule replacement. The reason I got up was because I've got a sample here somewhere. Not have unpacked it yet. We just moved the national office, but I've got a sample of the ore here that has the ruby red sphalerite growing on the silica. And you could get a pretty good, I was just going to hold it up to the camera, and I went over to my rock collection here and I haven't got it all unboxed yet. And it turns out it's still in one of the boxes. So I'm sorry I didn't get it out where you could see it, but it really is. Yeah.
I was interested to find this impregnation because that's what you see in the stratobound copper deposits. You see a lot of silicification of the host rock and not obvious precipitation of discrete silica associated with those deposits.
Yeah, it's really pretty spectacular. I see Matt has commented on the red sphalerite. This stuff it's like this dark ruby red, and it usually is doubly twinned. So it's almost circular. You wouldn't think it's a crystal, but because it's doubly twinned, it kind of makes those small, almost pencil eraser shaped, a little bit bigger than that. So in this sample, I was in Carterville, Missouri. I didn't realize I was trespassing, but I was. And the gentleman came out. When he found out I was a geologist looking for rocks, he was fine. But I had walked past the property line and there wasn't a sign there. Somebody had knocked it down. And so I stepped right over the back of it and didn't even see it. And he was very nice. But I picked up this sample that was just, kind of 1 in a million red sphalerite. So
Yeah.
The silica there, what would happen was the fluids were pretty low pH. And the initial fluids would dissolve a lot of the carbonate, and they would create a tremendous amount of pore space, often in sort of chimneys that followed these fractures or fault zones.
Oh, yeah.
And then once the pore space was there, as the rocks cooled, then the silica would get precipitated out. And so you would see this chalcedony precipitated out. And you'll see where the chert that was contained inside those limestones was insoluble. And so then you have a breccia that's basically a chalcedony or jasperoid cemented chert breccia. And for years, the geology club at Missouri State, I did my undergrad there, we would go to Carterville and we would collect as much of that cemented chert breccia as we could, and we would sell it to Ward Scientific because they put it in their supplies that they would sell to earth science teachers at colleges and universities all over the country. So if you saw a cemented chert breccia when you were in school, it probably got collected and sold and came right out of Southwest Missouri.
Murray Hitzman, who's a very well-known name to me, has any ideas where in the tri-state zone the highest copper values were?
Okay, so first off, I'm kind of fanboying a little bit here. I read so much of Murray's work.
Yeah, right.
My goodness, I can't believe Murray's even at this talk. Ooh, no, Murray, I don't know. I kind of grew up down there and I banged around the mined areas a lot. And when you're a teenager or in your maybe late teens or early 20s, those are places that you go to have a party because you can't party anywhere else. But what I do remember is seeing, if I was going to find chalcopyrite, I found it, there was a mining area off 7th Street. So 7th goes east and it comes into I-44. And so if you would get off I-44 on 7th Street, there were 3 little mines right there, and you could always find chalcopyrite in the spoils there. So I'm wondering if, maybe you could go back and see if through production records, if there were any, because by then I think in Joplin they would have been keeping pretty good records, kind of see what they had in terms of tonnages.
Okay, any more questions, anybody? Last chance here. We're 12 minutes over. I haven't noticed. So unless there's any more questions, I will thank Aaron very, very much for a very interesting talk. I have, on Aaron's recommendation, I once visited Pitcher and those huge tailings piles and the closed up town, completely abandoned. It's an amazing sight. So thank you, Aaron. And
Mike, I see Michael Adkins. I'm craving cake.
Okay. So, and thank you everybody for attending. So,
and thanks for having me, folks. I really appreciate it.
And so long. Yeah.